continue looking at 6.3 and 6.4. So still looking at exponential formulas. We're going to do a little bit of review of what we did yesterday. And as I just said a couple minutes ago, then we're going to look at some formulas that use exponents and exponentials and variables. Okay? One of them having to do with interest in a bank account. All right, so first thing, just kind of a reminder. What's the formula that we're using in these two sections for exponential functions? Starts out y equals, yep. Yep, y equals a times b to the x. Perfect. All right, now, again, another review. But if I asked you to compare y equals 4 times 5 to the x to just y equals 5 to the x, how would you describe how those two graphs compare? This is where you write that sentence that's almost the same every time. What would you write down? Yep. Yeah, this one has been stretched vertically by a factor of 4. So that's a question we kind of did in the homework last night. Now, how about this one? It's the same idea, but instead of a 4, it's a negative 4. So how would you describe what's happening in that one? It's kind of like the last one, but you're going to add one extra thing on the end. Yeah?
A vertical stretch by a factor of 4 reflected over the x-axis?
Yep. So that's a vertical stretch by a factor of 4, and it's been reflected over the x-axis. Perfect. Any question why you had to add reflect on that one? Okay, why did we? What was there that made it so we had to write reflect? Yeah? It's a negative. If you see the negative, you got to add this part that's in bold at the end. Okay, and you guys didn't have to write that down. Okay, we did that yesterday. All right. So now we are on the guided notes. All right. So what we didn't look at yesterday is what happens if A is a decimal, okay? Or what happens if A is a fraction. We looked at what happens if A was like 3 or 4 or 5, but we didn't look at what happens if you had something like this. What happens if the A is 1/3? Well, when the number was bigger than 1, it caused the graph to stretch. If the number is a decimal between 0 and 1, it's going to cause the graph to compress. So it's like it's going to squish it. So instead of stretching it, it's going to squish it. Now, to make it a little bit easier, we're still going to write the answer the same way. So if I said to you, I'm going to take this rubber band and I'm going to stretch it 2 times as much. Well, then that means it gets twice as long. But what if I said to you, I'm going to take this rubber band and I'm going to stretch it by half as much? What would that really mean is happening? If you take something and you stretch it half as much. Sophie, what do you think that would be? So if I said I'm going to take this rubber band and stretch it twice as much, it means it's going to stretch and get twice as big. But what if I said I'm going to take the rubber band and stretch it half as much? Anyone have a guess what that would mean? Yeah? it would become smaller, right? It's like if I said to you, I want you to, like if you're pulling on something, and I said, you're pulling too hard, I only want you to pull half as hard. If you really do something half as much, it's really making it smaller. It's going to make it less. So if I said I'm going to stretch this rubber band half as much, it means it's only going to be half the size it was. So when we talk about how we would write the answer to this, under the written like part, you're still going to write the answer the same way. The graph is stretched vertically by a factor of, and then you just write whatever A is. But just keep in mind, if you stretch something by, say, 1/2, you're not really stretching it. You're really shrinking because you're stretching by 1/2. So anytime the number that's in front is between 0 and 1, it's really shrinking. But we can still write the answer the same way. Stretched vertically by a factor of, and then fill in your number. Now, let's say that not only you had a number that was between 0 and 1, but then you made the number negative. What's the same rule as yesterday? If you had something like this, first of all, you would say a vertical stretch by 1/3. And remember what that really means. If you're stretching it by 1/3, you're really shrinking it. And the negative is going to cause a reflection over the x-axis. So there's no change in what the negative is going to do. So under the part that says written like, the two written likes on your guided notes today are the same as they were yesterday. Word for word, they should be exactly the same. Okay, so it says the graph is stretched vertically by a factor of, just tell me the number that's right there. And then, because it was a negative, add that sentence at the end that says reflect over the x-axis. Okay, so we'll try a couple together, and then I'm going to give you guys 4 to try on your own. Okay, so you don't have to write this one down. We're just gonna do this problem together. Okay, so if you were comparing that one to that one, what would be the sentence you would write down to explain how this graph compares to that graph? Well, Caleb, how would you describe how these compare?
They compare because x is the same, both of them, like it's being multiplied by the same, right?
Yep. So you gotta write a very specific sentence.
Mm-hmm.
Well, what would be the sentence you would write down?
Oh no.
Well, how did we do it? It's the same idea. If it was like, let's just do one we did from the homework last night.
Mm-hmm.
How would you do this one?
Oh, you write x and y tables, right? You should do that.
Only if you're going to make a sketch. This, we're just going to compare. So it's going to be one of those sentences that we had on the guided notes that says written like. And then we write the sentence. Okay, anyone help him? How would you write how this graph compares to the one on the right? Finn? How would you write how these compare? So think back to how we did like examples 5, 6, and 7 in the homework. This would be like one of those from last night. Yeah.
Graph and stretch versus by factor.
Yeah. So this is a vertical stretch by factor of 3. And that means that the graph is really stretching 3 times as much. All right, so now let's try this one. Y equals 1/2 times 4 to the x. How would you describe that one? What would be the sentence you would write? Yep.
Graph is compressed vertically by factor.
Well, make sure you follow the written like. You always want to make sure we go with what that says. So if you follow that, what does it say, right?
The graph stretch vertically of factor.
So vertical stretch by how much? Factor of
Or
1/2. Yep, don't even change the number in front to a decimal. Just leave it as 1/2. So that's a vertical stretch by 1/2. So that's how you write it. But can somebody tell me, what does that really mean? If you stretch something by 1/2. Yeah? You really made it smaller, right? If you stretch it by 1/2, you're really making it smaller, okay? But just to keep it simple, we're going to write the answer the same way we did yesterday. And it is correct. You can write the answer this way. Vertical stretch by 1/2 is perfect. That is how you want to write it. But keep in mind what it really means. All right. Now, what if I had one like this? Negative 1/3 times 4 to the x. Yep, what would be your first sentence?
the graph is stretched vertically by a factor of 1/3.
Yep. So just completely ignore the negative for now and write what you just said. Vertical stretch by factor of 1/3. And we have to add something else. Yep.
And reflect it over the x-axis.
Yep. And reflect over x-axis. Perfect. So there really is no difference in how you write these compared to what we did yesterday. Okay, so those were just like a couple practice ones. Again, I said you didn't have to write them, but now we'll do example 1, and I'll let you guys try those on your own. Okay, so the graph that we're comparing to is 2 to the x. It doesn't really change how you do anything. It just means every problem I give you is going to have a times 2 to the x at the end. And it'll have a different number in front. Alright, so let's go like this. We've got y equals 3 times 2 to the x, negative 3 times 2 to the x, 1/3 times 2 to the x. Can I get the last one? The last one is y equals negative 1/3 times 2 to the x. So it's always 2 to the x, but the numbers that are in front are 3, negative 3, 1/3, negative 1/3. Okay, so take a couple minutes and see if you can figure out the sentence you would write down to describe each one of those. Okay, so no graphing. You don't have to do a table. You're just writing a sentence to compare them. Okay, guys, let's look at the first one. y equals 3 times 2 to the x. How would you write down how this one compares to y equals 2 to the x? Yeah.
Vertical stretch by a factor of 3.
Perfect. So vertical stretch. And then you have to say by how much. It's basically stretching it 3 times as much. Vertical stretch by factor of 3. Perfect. Okay, let's look at B. So this one, similar to A, but it's negative 3 times 2 to the x. Okay. Caleb, how would I do this one? Yeah.
What was it again?
How would I do this one?
So if you write, so we're writing it out. Okay, so you'd say that it's a vertical stretch of negative 3, correct?
A vertical stretch of how much?
Negative 3. Wait, no, 3.
3.
3 because the opposite, correct? And it reflects over the x-axis.
So vertical stretch by factor of, and then the number that you always fill in there is a positive. If there's a negative, we're going to write a separate sentence about it. But just look at the number, and it's a 3. So vertical stretch by a factor of 3. And then you have to say reflect over the x-axis. All right. How about C? Y equals 1/3 times 2 to the x. Yeah?
That vertical stretch by a factor of 1.
Yeah. It's a vertical stretch by factor of 1/3. And it's a stretch by 1/3, which really means you're doing what? If you stretch something 1/3 as much. Yeah? It's really compressive. It's really a shrink, but we're writing it this way so it lines up with what we did yesterday. And again, this is correct. That's how you do it. Okay. And how about D? Yeah.
Stretched vertically by a factor of 1/3.
Yep.
Over the x-axis.
So vertical stretch by factor of 1/3 and reflected over x-axis. Yep. So any questions on that? All right, so let's look at an example now and see if we can come up with a formula. So I think you guys already have this under example 2 on the back. It says Noah bought 5 butterflies. So that's how many he starts with. And every year the number of butterflies triples. Write an exponential function that basically is going to represent the number of butterflies, say after 5 years, 6 years, or however many years we want to go down the road. Okay, so the first thing you have to figure out, well, they give you a hint. They say to make a table. And the table is going to have 2 columns. One column is going to be the year. And the other column is going to be how many butterflies did Noah have that year. Now, we're going to assume that when the butterflies triple every year, we don't know how many would be dying every year, so we can't really take that into account. We're just going to assume that the number just keeps tripling. Okay. So, the first year that we start with is the very beginning. What number do you think would represent the very beginning? It's almost like it's even before the first year. It's like how many he had right when he went to the store and bought. Think of like when you use counting numbers. What's the first number you think of? We're not counting whole numbers. Yeah, 0. So 0 always represents the time at the beginning of something. 1 represents the time 1 year later. So 0 is the beginning. And how many butterflies did he have at the beginning? Yep.
0.
Well, when this whole thing started, like he started with how many after he went to the store?
5.
Yeah. So at the very beginning of his butterfly collection, when it started, there were 5 butterflies in the collection. And then, let's go 1 year later. How many butterflies would you have 1 year later if the number of butterflies he has triples every year? Yep. Yep, that's it. 15. So he has 15. And then let's go 2 years later. How many butterflies would he have 2 years later? If it triples again. Yep. That would be if it doubled.
Oh, 35.
30.
Oh, maybe 45.
45, yeah. So 45. And then if we wanted to go 3 years later, we would have to triple 45 and use your calculator. And he'd have 135. So now the question says to write an exponential function. Can someone remind me again, what's the formula we use for an exponential function? Yeah? A times B Lexi? To the power of x. Okay, so we got to look at that table and figure out the A and the B. How do you get the A when you're looking at a table? Yep. Yeah, it's the value that's with 0, which in this case is what? 5. So your A value is 5. In other words, A is what we call the starting value. It's how many he started with. And how do you get B? Where does the B come from? Yep.
Like how many times it skip counts in this number?
Okay, so how would you figure it out for this one?
Multiplying by 3.
It's multiplying by 3. Because it's a times 3 each time, that's your B value. So what would be my formula that represents how many butterflies this person has if I fill my values into my formula? Yeah?
Y equals 5 times 3 to the power of x.
Perfect. There you go. Y equals 5 times 3 to the power of x. That's how you write a formula for a word problem like this. The easiest way is to make a table. You don't have to make a very big table, but whenever you're counting, I know I said you normally want to use like -2, -1, 0. It doesn't make sense to use negatives when you're talking about time. Because 2 years before he started collecting butterflies, he didn't have butterflies. So negative doesn't make sense. So with time, you always start with 0. Question on that formula? Okay, so in the kind of formula that we just wrote down, that was an example of what we call exponential growth. Exponential growth is something where you have a certain amount of butterflies, or it could be like bacteria, and it increases very, very quickly. So like if you start with 5 butterflies, and it triples every year. Watch how many you would have after just, say, I don't know, 10 years. So there's 1 year. There's 2, 3, 4, 5, 6, 7, 8, 9, 10. So just after 10 years, you have almost 300,000. And if you went another 10 years, it'd probably be in the billions, the trillions. So something that grows exponentially grows very, very quickly. Okay? And that can be a bad thing, like if you're talking about bacteria. Like if you have bacteria, let's say you have bacteria that triples every hour. Well, if this was bacteria that tripled not every year, but every hour, you'd have over 300,000 bacteria just in 10 hours. And then after a full day, you'd have billions. So it goes up very, very quick. Two things have to happen for something to be exponential growth. First of all, we have to have an A value that is greater than 0. And we have to have a B value that's bigger than 1. If we have a B value that's smaller than 1, we'll talk about that some other time, but that's exponential decay. That's where something goes down very fast instead of up very fast. Okay, so let's go to the formula. So now there's a box at the top of your back page, kind of in the middle. It says the following equation is used to model exponential growth. And that's the equation we want to write down. So in the box, you want to put y equals a times 1 plus r to the t. And this is a formula that's specifically made to figure out like how much money you're going to make if you put an investment in a bank account. Right? And there's 3 things that we have to know. The first one is A. Okay? A is like the number of butterflies we started with. In our last problem, A was 5. In general, A is how much you start with. Yeah. Yep. So A can be some kind of initial amount of butterflies or initial amount of bacteria, some kind of amount of money that you're starting with, but it's something you're starting with. R basically tells us how fast the money is going to grow. A lot of times when you put money in a bank account, they give you a percent. And they'll say, well, the percent interest rate on this account is like, 0.5%. Or, if you're buying a house, instead of you making interest, you have to pay interest, right? Because the bank is being nice enough to let you borrow their money. So you have to pay them. It's kind of like your mandatory thank you for letting the bank, use their money. So in that case, you might have an interest rate of like 4.5%, right? But the point is, it's usually going to be a percent. Now, if you had something that was a percent, how do you change 4% to a decimal? Yeah? 0.4 would be 40%. Yep.
4 over 100.
So, it would be 4 over 100 as a fraction. And if you actually divided 4 divided by 100, what would the calculator give you?
0.04.
Yep. So the idea is when you have to change, here's another one. When you have to change a percent to a decimal, which you do have to do in this formula, you have to write your percent as a decimal. You move the decimal 2 places to the left. If you move it back 2 places to the right, you change it back to a percent. Okay, here's another one. Let's say 12%. That would be 0.12. Move the decimal 2 places to the left. Right, so that's the second thing you need to use this formula. And the third thing you need is t. T is an amount of time, and the time is usually measured in years. So it makes a difference if you leave your money in the bank for 1 year versus if you leave your money in the bank for 50 years. You're going to make more money if you leave it there 50 years. So those are the 3 things: time, rate, an initial amount. Let's try an example with that formula and see if we can identify all the variables in this problem. All right, so it says that you're going to put $250 in a savings account that earns 4% interest. I'm just going to add one thing to it. We'll leave the money in the account. For 5 years. So let's not worry about the last part yet. Let's just focus on the first two. So I need to figure out A, and I need to figure out R. In the sentence that's typed, not the one that I hand wrote, which value there is my A? Yeah? Yeah, that's my investment. That's how much money I'm putting in the bank. $250. And which number there is my rate? It's my interest rate. Yeah? 4%. And remember what we said? It has to be a decimal. Actually, we already did that one. What is 4% as a decimal? Yeah? Yeah. 0.04. So here's your A. Here's your R. Take those two things and fill them into this formula. And that's the first part. So it's Y equals 250 times, this is always a 1. That 1 never changes. 1 plus, and it says to add R, which was the interest rate as a decimal, 0.04. And for now, just leave it as T. I know it said T is 5 years, but we'll come back to that. So Y equals 250 times, what do you get if you add 1 and 0.04? Yeah?
1.04.
Yeah, exactly. 1.04. So you do want to always add those together to the T. So that is the formula they wanted you to write down. So it's just like the formulas that we've been doing. Y equals A times B to the X. You just had to figure out what the B was. And the B is always 1 plus R. That's how you get the B. Now, how many years did they say they wanted us to leave this money in the bank? Yeah? 5 years. So if you wanted to figure out how much money you would have after 5 years, we would take 250 times 1.04. And what power would I raise 1.04 to? Yeah? The fifth. You plug in a 5 for the T. And if you do that on your calculator, you definitely need a calculator, you could figure out how much money you would have. 250 times 1.04 raised to the fifth. So if you leave your money in the bank for 5 years, and you don't touch it, and come back 5 years later, you'll have $304.16. About $304.16. If they wanted to know after 7 years, well, put in a 7. After 20 years, put in a 20. But that's the formula that you have to use to always figure it out. Any question on it? Let's try another one that's based off that one. Okay, to get these two on the same page, I'm actually going to delete this page so I can put this one next to the next problem. Does everybody have this page before I delete it? Okay. All right, so I want to keep the formula up there. All right, and this one, I think you already have written. It says, write an exponential function to model the situation. Well, this is the formula for an exponential function, so we're going to use this again. And then it says after you write your formula, we're going to use it to estimate a number after 4 years. Like in the problem we just did, we estimated it at 5 years. Well, this one they want us to do 4 years. It says the population of a school is 10,400, and it's growing at a rate of 3%. So we have to write a formula like this. What are the two letters that we need to figure out in my formula used? Yep. I need A and R. So looking at this, the A and the R are in that box. One of them we have to fix a little bit. Somebody tell me, what's the A? Yeah? Yeah, the A is an amount. It's an amount of people in the school. So A is 10,400. And what's R going to be? Just be careful because we need it as a decimal. Yep.
0.03.
Perfect. 0.03. So now it says to write an exponential function. Well, let's do it over here first. Y equals, we're going to fill in 10,400 for A, parenthesis, put a 1, plus, and what are we filling in for R? Yeah. 0.03. And the last thing I need is the T. Don't worry about filling in the T yet. That's the next one. So where it says exponential function, it's y equals 10,400 times, can someone simplify that for me? What's 1 plus 0.03? Yeah? 1.03. And don't forget your T. So that's your formula. And they want us to use the formula to predict how many students will be in the school 4 years from now. So where is this 4 going to go? It has to be plugged in somewhere in my formula. Yep, for T. Okay, so again, you definitely need a calculator for this kind of problem. But you just type it in exactly in the order you see it. 10,400. Press the times button. Put in 1.03. And the exponent we want to use is a 4. So that means after 4 years, there'll be about 11,705 students. Doesn't make sense to round students to a decimal because you can't have 0.2 students. Right? So we're just going to round it to 11,705. If this was money, then I would say, yeah, we could round to 2 decimal places with money, but not with people. Question on that one? All right, let's look at the last one. So the last one, it's pretty similar to the two we just did. They give you a formula to use, and all you have to do is fill in the letters in the formula. So let me give you the last one. Okay, so all you have to do is write down what's in the box. And make it bigger. Okay, so this formula has, the last one had 3 letters in it. This one has a 1, 2, 3, has a 4th letter. But they're going to tell you every one of these letters in the problem. The A is the same, so that's an initial amount of money. The R is the same. That's an interest rate. But remember, we have to write it as a decimal. The T is the same. T is the amount of time in years. The only extra thing that's in this formula that wasn't in the other one is this. I'll highlight it. That N and that N. That's the only thing that's different. So in this particular formula, you have to take R and divide by N. And you have to take the T and multiply by N. So what is N? Well, N is something that a bank would tell you. And it has to do with how many times interest is compounded per year. What does that mean? It basically means how often the bank puts money in your account. So when you make interest from the bank, how many times a year do they pay you? Do they just pay you at the end of the year? Or do they pay you with interest every single day? It makes a little bit of a difference. But it's not something that you have to understand from like a financial perspective. It's just a number that they're going to give you in the word problem. Okay, let's try at least setting up the last formula. And then maybe as a warm-up tomorrow, I'll have you guys finish. Okay, so we just have to go through and see if we can identify 4 letters. A, R, N, T. And all of that information is going to come from right there. Anybody think they see what A is? Yep. $240. That's the amount of money that we've invested. We can put a check mark so we remember that we used it. How about R? Yeah? 9%. But when we write it as a decimal, we get 0.09. Perfect. Let's jump to T. Does anybody see how many years they want us to do this for?
3 years.
3 years. So we use the 240, the 9, and the 3. N is the number of times it's compounded. It tells you right there, compounded annually. If something happens annually, how many times a year does that mean? Yep, once. If something happened monthly, it would be 12. If it happened daily, we'd use 365, even though leap years are 366. But annually means one time. So now let me just write the formula. 240 times 1 plus R is 0.09. And technically in this problem, you don't need N because N is 1. And if you divide something by 1, does that change it at all? No. We'll put it in because it might not always be a 1. And then it says N times T. 1 times 3. Okay. So now we just type that in on the calculator and that's our answer. Okay. We'll practice typing that in on the calculator tomorrow. So homework tonight is the 6364 worksheet, part 2.